So the shapes of the orbitals are what I drew before. These are the shapes of the 4 atomic orbitals. The energies are a different story. And to represent the energies, we draw them on a diagram like this, and as horizontal lines on the diagram is an orbital. Orbitals can only hold 2 electrons because of the Pauli exclusion principle, which says that no 2 electrons can have the same quantum numbers, and if you want to read more about that, check out the wiki. But to represent 2 electrons in a given orbital, we do so like that. The up arrow indicates a spin of plus 1/2, the down arrow minus 1/2, and lower energy orbitals are more stable, while higher energy orbitals are less stable. So keep that in mind as we're going through combinations and looking at both the shapes of the combinations and the resulting energies there. Before I get to that, I wanted to talk a little bit about also molecular geometry. So I mentioned last time electron pair domains, which are a critical concept that deal with the number of regions of electron density around an atom. We saw last time that there are only 11 ways to put electrons around an atom that has an octet, and there are really only 3 kinds of geometries associated with those 11 ways. So with 2 electron pair domains, we see the linear geometry. So for instance, a carbon with 2 double bonds on that carbon will have a linear geometry. And think about this in terms of VSEPR, which stands for valence shell electron pair repulsion, which is basically just electrostatic repulsion between the negative regions of electron density. They want to get as far away from each other as possible, so they form a linear geometry if there are only 2 of them. If there are 3 of them, the most favorable geometry is trigonal planar. Classic example of that is a carbon with 1 double bond and 2 single bonds. We see we have 3 electron pair domains here, and trigonal planar geometry. And then finally with 4, we have a tetrahedral geometry that results. Classic example of that is simply carbon with 4 single bonds. One thing I'll mention here in the context of geometry is that to represent bonds in 3 dimensions, we use wedges and dashes. So imagine the wedges coming out at you and the dashes going back away from you, and we always represent the wedges and dashes on the same side of the bonds that are in the plane. So in other words, don't ever do something like this. That drawing doesn't really represent a tetrahedral carbon. Tetrahedral carbon is better represented this way, and to see that you can build a model. The origin of these geometries has to do with a deeper theory than just the Lewis dot model. So Lewis dot model doesn't really tell us a lot about where electrons exactly are located in space and why, but molecular orbital theory does. So I'm going to transition now to talking about orbitals and why they're important and how we combine them to form molecular orbitals, which really key us into the geometry of molecules. Alright, so let's start with the basics. Combining orbitals. Well, the idea behind combining orbitals is that molecules want to spread their electron density out, right? The reason that forming bonds is a favorable process is because atoms want to spread their electrons out as far as possible in order to avoid electrostatic repulsion between the electrons in the atom. And that will stabilize electrons in those orbitals. However, we can also destabilize orbitals if we subtract their electron density or we add regions of opposite phase. So in the diagram up here you can see 2 orbitals, and you'll notice that these 2 lobes have the same sign. That's why they're both light, and these 2 have the same sign. And so both of these would add constructively, so we would spread the electron density out. However, if you had 2 orbitals that were combining with opposite phase, for instance, the situation here, these 2 would actually cancel each other out, this guy here and this guy here, and so we would actually constrict the electron density, and this will raise the energy of the orbital. In the wiki I mentioned 3 critical factors for orbital overlap: distance, energy, and symmetry. What we're going to do now is look at the atomic orbitals and look at their combinations and see how we would combine them and what that means both for their appearance and for their energy. So we're going to artificially bring them together, so we won't worry too much about distance. We won't worry too much about the energies of the orbitals because we're only dealing with atomic orbitals, so they're all pretty much the same energy, so we won't worry about those here, but we definitely will be worried about symmetry, because symmetry is critical in determining whether we're dealing with destructive overlap, which is what we see here, where the orbitals cancel each other out, or constructive overlap, where they reinforce one another. Alright, so let's get going here. So this sheet is one that will be posted on the website for sure, and it's one that you should go through on your own, definitely. But I just want to look at a couple of examples on this sheet and sort of how to go through doing it. So basically, this outlines for you every possible combination of one atomic orbital with another. You see the atomic orbitals up here with the plus and minus signs for each. On both axes, every possible combination is here. In order to show a combination, we draw an orbital around these black dots. So the first dot, think of it as atom 1. The second, think of it as atom 2. So for instance, the combination of this guy with this guy, we would represent by imagining the two orbitals sort of merging together to form a big blob of all light phase orbital density between those two atoms. And clearly this is a constructive example of overlap. It's an example of sigma type overlap, which I'll deal with a little more detail in a second, but basically that means that along the bonding axis, so along this bonding axis, we have an axis of symmetry. So if we were to look down that axis of symmetry, what we would see is just a circle of electron density forming that bond. And not all bonds have this property, as you'll see. But for that combination of the 2s with the 2s, that is what we see. Let's take an example of destructive overlap. So take the 2s and add it to the minus 2s. In that case, between the two nuclei, we'll actually see a depletion of electron density. So we would draw it this way. There's actually a region where there's no electron density at all, and we call that a node. Nodes are really important because they tell you where there's no electron density at all. So you want to look for both regions where there are a lot of electrons, which are enclosed by the orbitals, and regions where there are none, which is where we have nodes. What the node tells you is that this is an anti-bonding orbital. The reason it's anti-bonding is because it pushes the electrons out towards the periphery of the orbital. Between the atoms, there's not many electrons, so the atoms will actually want to actively separate from one another, assuming there are electrons in that orbital. If that orbital's empty, then there's really no problem for the molecule. So I would encourage you to go through some of these other combinations using those basic principles of combining the orbitals in constructive and destructive ways, and see if you can identify the properties of each combination.